Thank you, sir. So, on behalf of the Companies Committee, I welcome you all for the first session of 5-day faculty development program on additive manufacturing from 3D printing to factory floor. The chief guest, the speaker of the session is Professor P.M. Pandey. Professor P.M. Pandey is associated with Department of Mechanical Engineering, Indian Institute of Technology, Delhi. He has around 22 years of experience in teaching and research. He has obtained his BTech in 1993 from HBTI Kanpur, MTech and PhD from IIT Kanpur in 1995 and 2003. He has supervised around 43 PhD scholars, in which 13 are ongoing, and 35 MTech and 20 BTech projects. To his research credentials, he has filed around 16 patents and published around 250 research articles that includes peer-reviewed journals, conferences, and book chapters. He has undertaken 12 sponsors projects funded by DST, CSAR, DBT, etc. He is reviewer of research projects from DST and reviewer in 5 international journals. His area of research includes rapid prototyping and tooling, CAD/CAM, non-traditional machining, finite element analysis, biomedical implant using additive manufacturing. With this brief intro, now I request Professor P.M. Ponte to enlighten us with his insight of additive manufacturing with the title Fundamental Concepts in Additive Manufacturing. Over to you, sir.
Okay, so good morning, and let me start with my lecture on additive manufacturing. So I have 1 hour time, I think, correct? 11 o'clock we will be finishing. Okay.
Yes, sir.
So, sharing screens where this WebEx.
Downside you can see near to stop mute stop video, then you have an option.
I think this is you have to open this option, yeah, because
okay, it is not enabled. 1 second, sir.
Yeah, now it is enabled. Yeah.
Okay, sir. Sorry for that.
Good morning. Sir, mail for the same file with CPT.
So has it come now?
Yes, sir. Is it visible?
Just full screen?
Now it is full screen, sir.
Okay, so the title of my talk is on the additive manufacturing or 3D printing technologies, the fundamental applications in design and manufacturing. Okay. So here, like as I was just talking about in my inaugural speech, in the beginning, this additive manufacturing used to be a design tool. Like if you try to see the design process, the design process starts with the design need. And once somebody captures the voice of the customers in terms of design need, that is to be converted to technical specifications. And once you convert it to technical specifications, you can collect relevant designs. And after that, you go with the CAD process. So in the CAD process, you try with the design, then you model and simulate it, and after that, go for the analysis. And after analyzing the design, the successful product will only be the optimum product. So you go for optimization of the design. Now the optimization may involve today even topological optimization. So it's not only the optimization in terms of strength to weight ratio, or maybe the minimization of cost or minimization of some other aspects, but it may be even the topological aspect, that is the topological optimization. Now, once you have optimum design of the product with you, the next step is design evaluation. And the design evaluation means you have to make first few prototypes of a particular product and then you are going to, you know, uh, make those prototypes and test those prototypes. So that is called a design evaluation function. So this particular uh, technology is something in the very beginning it used to be used at this particular point. Now, once your prototype is finalized, your design, optimum design is tested, and it is found to be okay, the design communication and documentation is done. Means you make the blueprints of your design. And once you have finalized and you make the blueprints of it, you have to produce the component. By producing the component, you have to first plan the entire production process that is known as process engineering. So in process engineering, you not only do the process planning, but you also do production planning, design and procurement of new tools, ordering material, and if some CNCs or DNCs are involved, you are going to perform the programming action also. So once you are ready with this red box activity, which I call it as production process engineering, you go for the production. And once you produce, you have to control the quality, the packaging, shipping, and of course, the marketing. So once you market the product comes to the market, there will be again some critics, there will be again some review of the product, and in order to improve the product, you will again modify the design. That's why what happens, this design process, it becomes some sort of, uh, continuous process. And here it is the design evaluation, which is a very crucial step. And in the beginning, as I have mentioned, that this prototyping, which today we are calling very popularly as additive manufacturing or 3D printing, that was attempted or that was meant for this design evaluation purpose. So this prototyping or model making is one of the important steps to finalize a product design. It helps in conceptualization of a design. Before the start of full production, a prototype is usually fabricated and tested. So this manual prototyping by a skilled craftsman has been an age-old practice. So like earlier, the this particular activity of prototyping used to be in the hands of very skilled, very experienced craftsmen, means the skilled technicians who in the I will say in the guidance of some manufacturing or design engineers, they used to produce that prototype, and that's why it used to take very long time. Because these skilled craftsmen used to be very less in number. At the same time, because the product is new, their geometries may be complex, their materials may be difficult to machine, you will find that these things are not that simple. So the second phase of prototyping that started around mid 1970s or so, when a soft prototype model by 3D curves and surfaces was tested by in the virtual environment. So people tried, okay, why not to see for the uh, why not to go ahead for the virtual prototype typing. So they tried with 3D curves and surfaces, and this particular model was tested in virtual environment. People try to understand what is the behavior. But then the third and the latest trend of prototyping, that is the rapid prototyping, which has come into the picture where the material or the component is being built by layer material deposition. And this particular thing started around 1980s, and the first patent was filed around 1994. That was for a stereolithography process. So this has become possible because of the enormous growth in the computer-aided design, computer-aided manufacturing, mechatronics, automation technologies. The concept of product fabrication in 3D printing or in rapid prototyping is not that difficult. Like if you have to produce a product like this, you can machine the product. You can machine, and machining means you are removing the material in a very controlled manner, in a layer by layer fashion. Second thing may be that you can take the two blocks and you can join. The third thing may be that you can take a bulk of material and you can deposit, that is known as forming. Or the third thing may be that you can take a layer by layer material deposition, that in the beginning there's nothing, but it is a top up approach. It is a bottom up approach, that you are starting depositing the material from the bottom and you're going up. So this is how you are adding the material and you're able to get the output. So here, basically, the idea here is that you start with the digital model, that you will create a CAD model, correct? You will do the CAD modeling. After that, the CAD model, which is being uh, stored as a .py, that will convert to STL file. So it will be converted to .stl file. And after it is converted to .stl file, that is tessellated model, you are going to slice the model. So once you have done the slicing, it is nothing but the sort of layered model. So it is called generic layered model. This is the layer by layer information, and each layer has to be decided now. So for deposition purpose, you need a hardware. That hardware is nothing but a 3D printer or a additive manufacturing system, which is also known, earlier it was known as the RP system. And this RP system will be driven by this data, but there's an intermediate step that will be governed by some software that may be because of this data. So you need to calculate the laser deposition paths or material deposition paths, and you have to do this. So you have to, once you calculate this thing, this is being done in a process software. The software may be along with the machine, or it may be a freeware software, open source software. So you can drive this 3D printer and you get basically the component. And this component is, if it is found to be okay, you do the post processing. Otherwise, you go back and change the design once again. That's how this is a process chain. So here, like what I tell, that if this is my solid model, suppose, for example, I want to do this thing. This is the solid model I want to make. And this is the process of tessellation. So the process of tessellation can be understood by this figure. Here there's a, like there, this solid will have a number of surfaces. Some surfaces are planar, some surfaces are not planar, they are free-form surfaces, the way it has been shown here. So all the free-form surfaces which belong to this particular model, they are being approximated by small triangles. Correct? So these are being approximated by small triangles. You can see here that I have shown that this small portion of this free-form surface that has been approximated by this triangle V1, V2, and V3, and definitely then there will be deviation, because the curved surface is somewhere here, and once it is being deviated, so this delta is called the chordal deviation or maximum faceted deviation. So this deviation is something which is important to understand, because delta, as small as delta is, the approximation will be a better approximation, and smaller will be the size of the triangle, and therefore the number of triangles will be very large. More is delta means it is a poor approximation. You have very large triangles which will approximate and you away from the design. So this delta is something which is an important parameter which one has to decide that how really you are going to talk about taking the size of this. After selecting position orientation, the selected model is sliced. Now the next step is, one more important step is there, that how to deposit this component. I can deposit this component like this. I can deposit this component like this, or maybe in some other orientation. So that is another decision. And once that is being done, this model is being sliced. And how do you slice? You slice by basically this slicing is an intersection problem. So you intersect horizontal planes by this scale file, and once you intersect the horizontal planes with the once you intersect the this horizontal plane with the STL file, you are going to get these polygons, and these polygons are like this. So if you deposit the material from bottom to the top, you can see that this is how it is being. You basically get the nested polygons from bottom to the top, and these are the. Now here, if you really see this picture, you can appreciate that some of the slices are very fine. However, some of the slices are thicker. So this happens because you are going to talk about adaptive slicing, correct? So adaptive slicing means you are depositing in such a way that you are depositing thicker slices as well as thinner slices in combination, so that you are able to minimize the build time. At the same time, you are able to minimize the stepping effect, so that your surface is smoother. But in reality, you will not find any such system which is able to deposit like this. It means in one part, we generally use same slice thickness everywhere. Then generation of laser scanning paths or material deposition paths, that is another important aspect. So here we try to generate the laser scanning paths or the material deposition paths depending upon the kind of 3D printing technology somebody is using. If it is a laser technology, you will calculate the laser scanning paths. If it is a free FDM kind of technology, where there is a nozzle and the nozzle moves on XY platform, so you have to calculate the GM codes there, the material deposition paths to calculate. Then basically you go for the deposition. So for deposition, you need to have one hardware which will deposit, and this deposition, there will be some technology for deposition. This some technology of deposition means it will be either liquid-based technology, or it will be a solid-based technology, it will be a powder-based technology. So depending upon the situation, you try to select the different technologies for. After that, the important step is the post-curing step. In this post-curing step, you try to deposit, you cure, like in case of stereolithography, the part is not completely cured inside the chamber. So you have to take the part out and you have to put in some other curing chamber. So that is the post-curing. Then removal of the support structure is another important area. So you, because the removal, like you can appreciate that whenever there is an overhanging feature and you are depositing from bottom to the top, so you need to plan for the support structure. So this you have to plan for the support structure, and then you have to basically do the removal of the material, those support structures from the actual component. And because there may be requirement, you need to do the finishing by sanding, polishing, or painting in order to improve the surface quality, in order to improve the aesthetic, in order to improve the strength for the painting. Also, in certain cases, it may be in the metal spraying in certain cases. So what do you have? Like in this way, from the virtual CAD model, in a very short span of time, maybe few hours of time, you have your this 3D printed part. So that is what is called as the rapid prototyping. So we call these processes to be rapid. processes because of these reasons. Okay, now we have to see that what are the kind of data which can be taken or which can be used in 3D printing. So obviously the first one I have already told you, that is the 3D CAD. So this 3D CAD you use, convert it to STL and go for printing. There may be second, that is 2D CAD drawing that may be converted to 3D CAD drawing, and then you make STL and go for printing. There are two more ways. One is called reverse engineering methodology. So if you are having any old component with you, or you have some idol with you, you have some monument with you, you want to make exact replica of that thing. So what you can do the scanning of the particular uh, model, and once you uh, take the you scan the model, you get the point cloud data, and after getting the point cloud data, you do the reverse engineering. So reverse engineering means you have reverse engineering softwares. These reverse engineering softwares take this point cloud data as an input, and then you can recreate the 3D CAD model, and you can create the SQL file. One of the most important application is the fourth one, where we try to use MRI scan or CT scan as the input data, and then use that data for 3D and 2.5D reconstruction by some softwares, very special type of softwares, which are known as Mimics or maybe Simpleware. The software we use and use this DICOM files of MRI or CT scan as an input, and try to do the STL file, try to get the STL file, and this STL file can be used to drive any 3D printer in order to get the medical model. So this particular route, if you see, is biomedical application. So that's how we can see. It's all it's not. So there, in general, you can see that you can have CAD models, you can make a STL file, you have a point cloud data, you can reverse engineer, make STL file, or you have a MRI or CT scan data, and you can make a STL file, and you can proceed ahead. Then basically we have RP. So I have already told you that if you introduce this rapid prototyping, this as a product design tool in your product life cycle, then what happens is that this new way of model manufacturing that has potential to reduce or to compress the product lead time, that is from the time that starts from when you start thinking about the product till you talk about, uh, you talk about the launching the product in the market. So that time is known as product lead time, and you are able to see that that may be reduced up to 90% in certain cases. So what has been shown in various studies that this product lead time has been reduced to even sometimes as high as 90%, as low as 50% if you introduce this new method of model manufacturing as a product evaluation, design evaluation tool. Okay, now let us try to see the classification of these processes. So from the first row, you can see that over the time, like this RP processes were developed around 1995, like the first patent came in 1994. So they are not very old. They are as old as 25 years. So during these 25 years, many titles were proposed by the researcher, and they are available in the literature, like rapid prototyping, generative manufacturing process, layered manufacturing process, solid free-form fabrication, rapid manufacturing, and today, very popularly, we are calling them as 3D printing and additive manufacturing. So here, basically, if you see, uh, there are two categories. We do the classification of additive manufacturing process based on the initial material or the raw material which we use. So we use solid and liquid as the raw material. For the solid material, if we use let us start with liquid because we started with the liquid in 1995. The first patent which was filed was stereolithography. So we actually use some polymer. We use in the beginning monomer, and that monomer undergoes a polymerization reaction and that gets solidified. So this polymerization may be thermal induced polymerization. It may be a UV based polymerization or it may be a laser based polymerization where we have developed this stereolithography process. And the solid base, we have different technologies like I can use wire. So wire based system, I think most of you might have already seen, that is called fused filament fabrication method. And the second way may be that I can use powder. This powder may be one powder or it may be a blend of powder. And we have technology which is very popularly known as selective laser sintering. And even we can use foil. So if you are using foil, the technology is known as laminated object manufacturing. So I'll show you these things in my forthcoming slides. Okay. So if you have any question from this part of my presentation, you may ask, then I will proceed. Yeah.
Participants, if you have any questions, you can put so that professor can explain and move further.
Question? Hello.
Sir, I think participants are very clear with your explanation. So
Participants are?
I think they are very clear with your explanation. They don't have any questions. He thinks like you can proceed further, sir.
Okay, so now let us move to the processes. So these processes are like stereolithography is the first process which we talked about. So the process is shown in the schematics of the process is shown in this figure, in this diagram. So basically we have a vat, and this has a platform. This platform can move up and down with a resolution that is one layer thickness. And what we do, we pour photosensitive resin. So there are photocurable resins. They are basically monomers in the language of chemistry. So they are liquid monomers and their property is such that if light above certain threshold frequency falls on this liquid, there is a free radical formation and these radicals start connecting with the neighboring radicals and they form a very long chain molecules, which is nothing but a polymer. So we have, this is known as polymerization, photopolymerization reaction. And the concept is related to we can say photolytic reaction. So here we have this thing that on this platform, we first pour the monomer liquid equal to only one layer thickness. And then laser comes from the top and there are movable mirrors. So these movable mirrors will rotate and they will start and the laser spot will travel like this. And wherever the laser spot will go, below which there will be a polymerization reaction and you will get a solid voxel formed. Now, once one layer is being done, this platform goes down by one layer thickness and again you pour the this liquid monomer equal to one layer thickness and similarly the process is repeated there's a laser and this movable. So this movable mirror is actually a galvano mirror, which is a numerically controlled mirror. So once you have already calculated the information of the with respect for this layer, so based on that, this movable mirror rotates, and you are able to actually put the this material when this laser spot moves on the layer, the material is polymerized, and you are you get the hard layer. Now here, one more thing is to be observed, that if you need to have, this overhanging feature made, you need to develop the support structure also. So this is how we go and make the support structure. So the stereolithography is an important process because it was the first process which was developed in the beginning in 1994. The first patent was filed, and the good things about this process is that its resolution is quite good because the surface quality is also good because you are dealing with a liquid, and liquid can be spread in very thin layers. At the same time, you are having this limitation in terms of number of polymers or number of raw materials which can be used in this kind of printer, because the list of photo polymers is definitely very short. Now, the next one is the selective laser sintering process or melting process. So this is a powder bed technology actually. This is also known as powder bed technology. Now, what do we do here? We have the powder feeders. So we use very fine powder of polymer. We call it, in the beginning, it is called SLS. SLS it is called because of the polymers, and when just because of the reason of IPRs, and SLM, it is called SLM, selective laser melting at that time. So we spread one layer of powder on this, and then the laser comes from the top, and the laser scans the areas where you want it to be solidified. So basically, this sintering is unlike the conventional sintering which you study in powder metallurgy process. That is not the case here. So here these particles, they form neck to neck. There's a bonding because they are melted at their peripheral areas, and because of the surface tension, there's a flow of polymer and there's a bonding. So that's how the solid this is being solidified, and after that the platform goes down. You again recoat, and again the laser comes from the top, and you do it. So with this figure, you can again understand the process of SLS. There's a powder spreading by recoater, and there's a powder bed exposed by the laser beam, and then you are having this platform moving down, and then again there's a recoating for the next layer. So here, this brown color material is something which is called which is a sintered material actually, or solidified material, and the yellow color powder is a powder which sits there. So in this technology, there's no need to plan for the support structure. That is one of the advantages of this technology. And then another advantage is that it's quite versatile in terms of material, because you can plan for different materials. You can experiment on different materials provided it is available in terms of powder. And if we are using it for polymers, we call it selective laser sintering. And if we are using it for metals, we call it selective laser melting. And definitely for materials, for metals, the temperature ranges will be quite high. They will be as high as we can say up to maybe for maybe 1300, 1400 degrees Celsius, because in case of metals, you need to sinter, say, stainless steel, cobalt chromium steel for making implants, titanium medical grade alloy for making implants, even Inconel as a super alloy. So all these things you try to, sinter. So that's why the temperature ranges are up to 1300 to 1400 degrees Celsius. But in case of polymer machines, that a maximum temperature that it goes is around 300 degrees Celsius, because polymers melt like that only. Then we have another 3D printing process, which you all know. I believe you all understand this process. Most of you might have already seen the process, correct? Yeah. And this thing, we have basically, the process is like this. There are polymer spools. So these are ABS spools, and these wires are around maybe fine wires, and they're drawn in by the counter rotating rods. So there are counter rotating rods which draw these wire in, and once it comes out, you are able to deposit the material the way it has been shown, and this is called molten ABS. So this is XY control, and this is how we are able to deposit the material. And generally in the machine, you'll find that there are two nozzles. So the one is for the main material, that will be ABS. Most of the time we use acrylonitrile coated styrene as a material. There will be polyvinyl alcohol, that is another material. Correct? PLA, polylactic acid, that is another material. So we have a list of, some people have also tried even a high temperature polymer, that is called PEEK. That is for making some spinal vertebrae, etc. For making spinal implants, people have even used PEEK, which is a biocompatible polymer material, which is quite strong, as well as its melting temperatures around 450 degrees Celsius. So people have even tried PEEK with this kind of printer. So, but the drawbacks of this printer is that its resolution is low, and the surface quality is poorer, rougher, and, and that's why its resolution is definitely quite low. The number of materials are also not that high, it's limited only, I'll say. So that's why though it is a very economical printer, and most of the places you will see only this kind of printer. So that's how this is also one of the important things. Okay, then we have this long laminated object manufacturing. So as I indicated you when I was talking about classification of these processes, so I told you that there will be sheet. The solid material may be in the form of sheets. So once it is in the form of sheets, what do we do? There's a platform on this platform we adhere uh, this particular thing, uh, roll on this, and then there's a roller, laminating roller, which rolls it from the top, and then we have this laser. So the function of laser here is to cut the material. In this case, the laser doesn't deposit. It doesn't, try to deposit the material. Rather, the function of laser is to cut the material. And if you really see this annular ring, the annular ring which you see, it is something which is related to the component, and all other portion, this is the hatched portion, it is not related to the component. So finally, what do you get in this process? What do you get? Like you are going to get, if you keep on depositing the material, you are going to get some sort of box kind of thing with you. And once you get the box kind of thing, you have to actually remove these small cuboids by some mechanical means, and whatsoever is left is your prototype. So this, from this concept itself, you can understand that you cannot make very small prototype. You can incise them. The features may not be very fine. So that's why most of the time you are using this prototype for making mock models. Okay, then let us move to the latest technology. One of the latest technology, which is called as direct metal deposition or direct energy deposition. Like there has been number of, this is a metal printer actually. So there has been number of parallel developments, and I can suggest you that the one such parallel development was with India National Laboratory. In 2006, they have brought this technology, which is known as laser engineered shaping. It is a powder blown technology. There was another development, parallel development at Michigan University. They called it as direct metal deposition technology. So here what happens is that there's a powder that comes down like this, and then you are basically depositing the laser, and the laser is coming from the center, and there's an optics in between, and once it focuses here at the focal plane, the powder streams and the laser and gets melt, and then by XY control you are able to deposit the different kinds of structures as it has been shown in this particular slide. Is it clear to everybody? So here the good thing about this process is that you have like I can have one material from this side, another material from this side. Generally, there are four such channels. One is here and the back of it. So different materials can come down from different sides, and even their flow rates can be controlled. And that's why you are able to fabricate the compositional functionally graded material. Like when you are depositing, you are able to change the composition of the material, correct? And so then you can also make the lines which can take the loads. So that's why what has been reported, like I have read some papers based on lens, they report that very fine microstructures can be produced by properly controlling the process parameters, as well as the strength of the components is also some, you will find that it is very, very nice in the sense that it is sometimes as good as forged components. So this is how we go ahead with this laser and shaping process, which falls in the category of direct energy deposition. So you can see that this is the interface. Like this is the nozzle of the lens, and the powder is coming from the center, lasers coming from the center, powders coming from the sides, and you are able to get the worn part repaired. So this is a technology which can even be used to repair the worn components. Is it fine? Now, this is the process interface for a this powder bed technology. So this powder, yeah, there was some question, I think. Uh, Somebody has written something. Let me just see. Yeah. So there was some question, I believe. Okay. So this laser, then this is the process picture. Uh, and for a powder bed technology, that how really laser interacts with the powder, and then we have selective laser melting, powder bed deposition. So, okay, and this is how the component is being made. Okay, now let me go to the some important processes, that is advanced EM processes. Yeah, so was there is any question before really I proceed?
Just
I
respond
would,
to him. Yes, sir, there was a question here. What
yeah.
what errors can happen in tessellation process?
Hmm?
What error can happen in tessellation process? Tessellation.
What else can happen means I do not understand the question.
Actually, there is a participant who has put this question in chat box.
He should, you please ask him to clarify the question. What
Yes, sir.
else? I do not understand what exactly he means.
Okay, sir. I'll just ask him to. Sir, you can directly ask to sir, what errors can happen in distillation? That's what the question is.
Good morning, sir.
Yeah,
Yes, sir. I wanted to ask what errors can happen when the
errors.
creation of yes, sir.
What
Errors.
errors? Error is a different thing. Like you can have, say, like if you really want to understand the limitation of the process, they may like the surface quality is definitely not very good. It's poor, I'll say, and the accuracy is also low as compared to the powder bed fusion technology. So that's my comment. Error. I do not understand. What do you mean by error?
Sir, like when STL files are created, then there are normal vectors for each of the triangles.
That is STL file error. That is a STL
Yes,
file error. That has nothing to do with lens here. That will happen with any process. Correct? That is a data preparation time error. So
yes,
that is a different issue. It's nothing to this. That is nothing specific with lens process. Correct?
and sir,
Now let us
yes,
try to see another 10 minutes the advanced processes. There are some videos also which you can appreciate. So let us try to see this direct energy deposition process. So this is a lens kind of process only, like the powder moves down from here. It's a powder blown technology, and this is a laser. The laser comes down, there's optics in between, and there's a focal plane. And here it melts and it is being deposited on XY control. So you have infrared camera. Definitely, this whole thing will be done in inert gas atmosphere because you have to have you don't want that material to get reacted with the atmospheric oxygen or nitrogen. You have this thing, that thing. So anyway, so basically this is how the process goes. So you can see this video. Okay, so this is another video you can see here. You can see this video here. This is another illustration for the same thing. Okay, so this direct energy deposition processes, they are suitable for fabricating multi-graded materials, large size parts, and high performance coatings also. So fast build and rapid material deposition, fully dense parts can be produced, and there is no need to support structures and can be used for repairing. But at the same time, you have limitations like poor surface quality, significant post processing, and part complexity is limited. So this DAD kind of process has number of this thing, that is application areas include aerospace, automotive, repairing of parts, nuclear, etc. Then we have LMD, that is the laser metal deposition process. Similar kind of process is a production nozzle coming the powder streams and later from the center it is depositing layer by layer. So there have been many parallel developments with little changes here and there. So here the challenges are that there's a complex process structure property relationship. The part exhibit very complex thermal histories, there's anisotropy, and these processes are quite uh, expensive. But at the same time, you get near net shape component, the complex parts can be repaired, the heat defected zones are small, distortion is lower as compared to other processes. Then we have this electron beam additive manufacturing. That is another important process which is called EBAM, electron beam additive manufacturing. So it is again a powder bed kind of process as you have seen SLM, but instead of having laser, you are having a electron beam gun which generates high power and it is as high as 3 kilowatts, and the beam melts each layer of powder with desired geometry, and this process is done in vacuum. So it eliminates impurities and yields excellent material properties. Then basically we have this an electron beam serves as an energy source. Now there's another variant of EVAM. So instead of having powder, you are having a wire feeder and there's an electron beam, and you're able to deposit the material as it has been shown here. Then so you can see that these are the different areas where this process is applicable, and there's a different applications of this process. Then we have wire arc additive manufacturing. So the people have also used welding process to go ahead with this. So you can see this video. It will explain that how big kind of process is being used to deposit the various features. Correct. This is called as, this is again a technology which is classified under direct energy deposition. So there's another video you can see. So you can see the kind of surface which is being produced in case of wire arc additive manufacturing. The limitations are the high stress distortions, residual stresses, shielding gases are needed if you want to work with highly reactive materials like titanium. There's a low emission and poor surface quality, but at the same time you can have wide range of deposition rates. And conventional machining time reduced to minimum, reduced lead times, etc. These are some components, the parts which have been produced by RAM kind of process. Then this is called multi-jet fusion additive manufacturing, made available recently by HP. So here the idea is that you use one go, this is also for plastic process. So here we use detailing agent as well as fusing agent. They are chemicals basically. So you can see here that we are using two kinds of agents, detailing as well as fusing agent. And in one go, you are, putting the light source. So this is wherever this chemical is there, you will find that there's a tuning. So so you can produce different kinds of components. This is a polyurethane flexible component. So this is a polyamide but strong components. So you have different components with very fine quality, surface and accuracy that you can get in this kind of printer. Then we have DLP printer, that is digital light projector 3D printing. So this is again used monomer, but here the concept is like this. Correct. So this is how we go ahead with this thing. So this is what is DLP printer is. So here this is stereolithography. So same, 40 photopolymer resin we are using. In case of stereolithography, it is a laser spot that moves. But in this case, the complete layer is, exposed by this light in one go because we are having some sort of projection system, which is like, movie theater. So this will be very fast printer if the uh, sections are large, but if the sections are very thin and you have integrated details, probably SLA may give you the better accuracy. These are the different, components which have been produced by this DLP printer. Then TPP is another process. Two-photon polymerization reprinting technique is another technique. So here basically the concept is that you have a chemical laser. And in this zone, you have a lot of intensity. So if you focus the laser like this in a photopolymer kind of situation, you can generate a very small voxel of as small as 100 nanometer size. So it has high resolution complemented with photon photomicroscopy, online process observation, and it has and you can do the polymerization in the presence of biological cells and tissues, provided we have biocompatible initiators and monomer with no toxicity. So it has applications in various domains of engineering. So these are the good things you can see. These are the micro prisms. So you can see the dimension. This is a micro lens. This is the scaffold. So dimensions you can appreciate, and these are the micro needles. You can appreciate the dimensions which are there. So we also have one printer to make composite. So how do we make composite? It is like FDM printer only, but you have fiber spool as well as the nylon spool. So deposits alternatively, and sometimes in a material like onyx, you have chopped fiber along with the nylon so that it is able to deposit. Correct. So you have basically functional components made by this printer, the way it has been shown here, like it is a shock absorber, it is a jaw for holding purpose in machining, it is a printed carburetor, etc. Correct? So with this, I'll stop my presentation here and let us, if you have any questions, I can take up those questions.
Participants, if you have any questions, you can go with that.
Yeah, you can, how to unshare this screen. Yeah. So now you can ask the questions if you have any question.
Sir,
Morning, sir.
in laser-based additive manufacturing process like lens and DED, sir, can't it happen that the nozzle gets blocked due to
No,
deposition of the product?
no, it will not happen. We have provisions for all these things. These are practical problems. It can happen also sometime, but these are industrial processes. People are using them in industries. So problems will definitely come. You cannot say that no, that it will not block. That cannot happen. It always happens. But there are remedy for that also.
Good morning, sir.
Ah.
The parts which are produced by using lens technology, do they also need to be sintered?
No. You don't need to center them. Any other thing?
Participants, any other questions? All right. If no further questions, we'll wind up the session. Thank you, sir. Thank you very much for enlightening us with all your experience. What are the things in a basic fundamental way, how people can get inspired towards additive manufacturing. It was so useful and so meaningful. Like the startup session, it was giving a bunch of information about what are the different aspects of additive manufacturing. Thank you very much for that, sir.
Okay, so thank you. Thanks a lot for this invitation and opportunity. Yeah. So I'm closing this session. Okay.
Thank you, sir. Thank you. Participants, you can join that YouTube link for common inaugural right now. So followed by that, we'll have our next session in the afternoon. So as we have this common inauguration, which was not planned fair, like we'll join the common inauguration right now. And before that, please fill the feedback forms, because each and every session you have to fill your feedback form to mark your attendance as well. As it was clearly given, almost you need 80% of attendance and 60% of mark from exams. So please join the session on YouTube live. We'll have the next section by 3 p.m. on computerized wire arc additive manufacturing by Dr. Swaroop Bhatt. The session scheduled at 11 for Dr. Vinod will be postponed to day 3, because like now we'll be having that common inaugural. So that session will be postponed to day 3. Thank you.